One second, I'm going to check on YouTube and make sure that everything is going as planned. Why isn't it my channel that pops up immediately? I can hear my voice. Hello, everybody. Hopefully you can hear me. I'm filming this in a meeting room that's next to a kitchen. And I don't know if you can hear the kitchen rattling, but this meeting room has the acoustic soundproofing of like a styrofoam takeout container. So my apologies if you can. And also my apologies for being bad at time zone math. I definitely made a gate posting error, and I'm sorry, and that's 100% on me. But thank you for hanging out and coming to join me. All right. Are you guys hearing that? Are you guys hearing that little bit of an echo? I'm wondering if that's just on my end in my monitor, or you are also hearing that. Hopefully not. Hopefully that's just me. All right, let's get started. So we were talking about multitask reading. Sorry, this is driving me nuts. I'm gonna have to find the window where it's in. There we go. Okay, you guys can't hear an echo. Excellent. Excellent. That is really good to hear. We were not talking about multitask reading. We were talking about multitask deep neural networks for natural language understanding. And the sort of general idea is a little bit similar to some of the other papers we read recently, like BERT, where you have a big model that works for a lot of different things, and you have sort of a smaller model on top of it. But the big difference is that this model, we are training using multiple tasks. Sorry, the clinking is driving me nuts. So we've got the model here, and we will be doing one type of task at a time. So we read last time about how the various tasks in GLUE, which is a big meta task data set, was assigned to each of these. And interestingly, the pairwise ranking for this natural language inference seemed to be the one that was most unlike the tasks that most unlike the ones that were it was the weirdest one. It was the one that they sort of picked out and treated differently because they said that it worked well and they had empirical evidence that it worked well. But that doesn't necessarily, I don't know. I would like to hear more about their other things. Okay. Where were we in the paper? And my apologies. I'm a little bit out of it. I'm pretty jet lagged because I've been traveling a lot and I had back-to-back travel, and I am bad at time zones also. Okay, I think we had read through this task section and we were starting with section 3 and potentially in the lexicon encoder, but I think it's, okay, yeah, we definitely read the lexicon encoder. I remember this because it was just like the BERT model where every input has this CLS token that's the label for the specific thing that it is. And then if there are multiple sentences or multiple things that are put in, so for things like the pairwise rank similarity, there's a separator token between them. So that was just like BERT. And then they use a multi-layer bidirectional transformer. So they're using just the encoder. If you remember from the Vaswani paper, they proposed a encoder-decoder model, so much like you'd see for other sequence-to-sequence tasks. And we're using just the encoder here, so like the first half of that. And we're mapping the input representation vectors, so the ones that we've created using the lexicon encoder here, into a sequence of contextual embedding vectors. So here's where we're adding the attention for this fully attentive network. And then, so D here is, I remember us trying to figure this out last time. D, I don't remember if we figured out where D was coming from. And then N was M is, I think these are from the original architecture. So D is like is specified as a hyperparameter, and I think M was as well, if you guys remember. I kind of don't remember. But we can go and look that if it becomes super relevant. So the shared representation across different tasks is this bit here. So everything up to the context embeddings. And this is being updated by each of these tasks. So we're doing one task at a time, and each of those tasks is updating all of the information in the L2 and L1 layers. And then this, I think this is just sort of like a sorting part. So this task specific layer, I think, is sorting which thing we're going up into. I'm not entirely sure if that's the case or not. But again, we should be able to see as we go through. Okay, unlike BERT, that learns the representation via pre-training and adapts it to each individual task via fine-tuning, MT-DNN, multitask deep neural networks, learn the representation using multitask objectives. So that's what I was saying. Instead of training this using one thing and then building this separately for each task, we're training all of this in one big go. So it probably, I wonder if it takes longer. It probably didn't take longer than Big Bird did to train. Big Bird. It sounds like Big Bird, which is another Muppet. And hello, everybody who's saying hi. Oh, Ahmed says M is the number of tokens and D is the embedding dimension in transformer encoding. Thank you. That's very helpful. So M we are getting from, oh, I see right here. It's literally directly in front of me while I was being like, I wonder what AM is. And then D is the dimension. So I believe that we specify that in the model hyperparameters. So that's something you pick. And then we didn't talk about the green layers here. So now we're going to find out what's in there. So single sentence classification output. So each of these are going to have a different target, and they're going to have a different loss function as well. So single sentence classification output was what we used for the tasks, including predicting whether an English sentence is grammatically plausible. So these were sentences that were like not things a human would say, like they're syntactically weird. They do things like violate WH islands, which I remember vaguely from my graduate level syntax work, and I don't especially recommend diving into the literature in unless that's something that you're already interested in. And this one, which is just a sentiment detector. So sorting an individual sentence. All right. So we are looking at the contextual embedding of this label token, which, oh my God, someone's making espresso. I'm never booking anything in this room again, which is very easy because I don't work out of this office. Which can be viewed as the semantic representation of the input sentence X. So this is the vector representation of our label. And then this is the sentence sentiment task. So the probability that X is labeled as a class C, i.e. the sentiment, is predicated by a logistic regression with softmax probably of C given X. So the probability of a label given a sentence is the softmax of big W transpose SST and the dot product with little x, where WSST is the task-specific parameter matrix. So we take the softmax of the task-specific parameter matrix and the contextual embedding, and then we take the softmax of that. So that seems pretty straightforward. That's what I would do for that task. Sorry for saying math words bad. No, I don't need to apologize. Thank you for your patience with me saying math words bad. I'm sort of self-taught with a lot of my math. All right, and then text similarity outputs. So these are tasks like, scroll. Given a pair of sentences, a real value score indicating the semantic similarity of two sentences. So we might say is one, well, it doesn't actually specifically look at paraphrasing. So I imagine that it would score I like ice cream and I don't like ice cream to be extremely semantically similar, even though they're not paraphrases of each other. But they have a lot of the same words, or like I like ice cream and I hate gelato to probably be pretty close to each other as well. Gelato is like ice cream. Okay, so suppose that thick X, I don't know what to call this, bold lowercase chi maybe, is the contextual embedding of CLS. So again, they're using the contextual embeddings of the label token, basically, which can be viewed as the semantic representation of the input sentence pair x1, x2. So in our training data, this is the degree to which the two sentences are semantically related. So I'm guessing if the two sentences are closely semantically related, we have a rating closer to 1 maybe. And if they're not very related, so like I like ice cream and it's fun to go tubing on a river, are not especially semantically related, we'd have a score closer to 0. I don't know that those are the bounds, but that's how I imagine it works. And then we introduce a task-specific parameter vector, WSTS, to compute the similarity score. So here, instead of a task-specific matrix, we are using a vector, and we're taking the dot product with the contextual embedding. And then G is this function, which is a sigmoid function that maps the score to a real value in the range of 0 to 1. Okay, so instead of taking softmax, which gives you the most likely category out of all of your categories, here we're getting basically a probability of similarity between the two, where 0 is not related and 1 is. Sasi says, hello, elite admission to the group, but I want to know, is this a transfer learning model? I don't know. My guess, we haven't finished the paper, my guess is that the authors are going to argue that you can use it for transfer learning if your task is one of these 4 types of task, and that this is sort of a general way that you could do additional fine-tuning if, say, you had an additional pairwise text similarity task. Yeah, that's my guess, but I don't know. I think it would be more correct to say that it's a multitask learning approach that maybe you can use for transfer learning. Roman says, sigmoid equals softmax for binary classification. Yeah, that makes sense. Thank you, Roman. And Sujay says, I want to know when you'll upload the video of API creation. So I'm not super involved in that. I don't think I've said that yet in this stream, but I think we're aiming for early summer to be able to release those. So we'll keep you updated. We're not just gonna like silently upload it and then not tell anybody. I'll announce it on my Twitter, and we'll probably announce it on our YouTube channel as well. Okay, so that's text similarity output. So they're basically doing the same thing. They're learning, here it's a matrix, here it's a vector. They have a learned set of weights that they apply to the label contextual embedding of the label. Here they take softmax, here they take a sigmoid function, and then that's the similarity, and then here it's the probability. Okay. So I'm picking up what they're putting down. I think this seems very reasonable. There's nothing here that I would consider super surprising. All right, pairwise text classification output. Take natural language inference as an example. The natural language inference task defines here involves a premise P of M words and a hypothesis H of N words. So they're different lengths, and they may or may not mean they may or may not entail each other, and aims to find a logical relationship between P and H. And that's logic in the terms of like formal logic. So entails, contradicts or has no relationship. So I like ice cream has no relationship to I like to go whitewater rafting. But if my whole family likes to go whitewater rafting because I'm part of my family, that logically entails that I also like to go whitewater rafting. Or my whole family hates going whitewater rafting because I'm part of my family, that contradicts that I love to go whitewater rafting. I've never actually been whitewater rafting. It's just super rainy in Austin right now, so I'm thinking about water things. Okay, logical relationship. The design of the output module follows the answer module of a stochastic answer network, Liu et al. 2018a. That's the same first author as this paper, right? Yeah. Okay. I'm pretty sure we looked that up. I'm not saying that everyone who has the last name Liu is the same person. That seems like it would be quickly found to be false. Stochastic answer networks, which I've never heard of, by the way. That doesn't mean they're not a major advancements in the field. It just I haven't done a lot with question answering. A state-of-the-art neural natural language inference model. SAN's answer module uses multi-step reasoning. Rather than directly predicting the entailment given the input, it maintains a state and iteratively refines its predictions. Okay. The SAN module works as follows. I just looked at the rest of the paragraph. This is gonna be a doozy. Okay, we first construct the working memory of premise P by concatenating the contextual embeddings of the words in P, which are the output of the transformer encoder, denoted as thick M to the pth power, is a set of real numbers of size dm, where m is all of the tokens? No, m is the number of tokens in P. And then D, I believe, is defined manually. Okay, so we get the output of the transformer encoder. And similarly, the working memory of hypothesis H, denoted as thick M, I don't know, fat M to the H, is a set of real numbers of dimension D. So that's going to be the same D, and then N. So the number of words in N. Okay. So basically, they make two matrices, one for P and one for M, from the contextual embeddings that they learned earlier in the model. Okay, then, and this is the math that's new to me, we perform k-step reasoning on the memory to output the relation label where k is a hyperparameter. Okay, we perform k-step reasoning on them. Okay, so they specify what k is going to be, that there's going to be so many steps. At the beginning, the initial state S0 is a summary of fat M to the 8th. Ahmed says the amount of mathematics symbols on this page is really high. It gets worse. Oh no. Okay, we'll get it. We'll work through it together. Okay, so we start with, okay, so we've got, so P and H are two, P and H are two sentences basically, and then we start with just saying that the relationship between P and H is H, and then we want to get to the point where we have where we pick from one of a set of logical relationships R, which I'm assuming is predefined, because the only logical relationships in the NLI data set are entailment, contradiction, and no relationship, or whatever the third one is. 0, null, ain't one. Okay. So we start with being a summary where we sum over alpha for every member of M, where alpha is a lot of linear algebra. Okay. EXP. Exponential. So this is, I'm assuming, a learned weight. Did we learn about little w rather? Have they mentioned it previously? I'm assuming based on this, that this is a task-specific parameter vector, maybe, of length 1, maybe? Roman says, that's just softmax, FYI. Oh, this is softmax? This whole thing? Okay, helpful. So they're taking softmax, and then they're dividing it by the, oh wait, okay, I see. So it is for each of, so we're taking the softmax for each of the possible categories, of which there are 3. Does that sound right? So this is softmax given learned task-specific, probably a learned task-specific vector. Oh, Saucy says the whole thing is softmax. Okay, I get it. So they are summing over the whole sentence, so the hypothesis sentence, the second sentence, where you're trying to figure out what the relationship is for the first sentence. Okay. And then they are, so they're doing softmax for each of the possible outputs, and then they're summing over it. Does that sound right to you guys? I'm so glad you're here. Otherwise, I'd just be staring at this, making stuff up. Where did we get J from? Do you guys remember where J is from? Because I definitely see it here, and I don't remember defining it previously. And it doesn't show up in any of the other, it's not in here. For J. So maybe J is for each of the hypotheses, I guess. Okay, at time step K, because we're doing this multiple times, K times specifically, in the range of 1, 2 through K minus 1, okay? The state is defined, oh, so the final K is the final step, and that tells us what our output is going to be. Roman says J is in the SO definition. Oh, I see. Okay, that's what we're summing over. Thank you. The state is defined by S to the K grew. S through K minus 1, and the next K. So this must be X is the contextual embedding that we get in. So we're combining the current step with the previous step and our context embedding. So we're sort of like re-feeding in the context embeddings at every step is what I'm getting in from here. I got no idea what GRU is. I've definitely heard this before. That's helpful. Help me out, Wikipedia. Disambiguation. All right. Let's see. Gated recurrent unit. Okay, that's probably what it is. It's probably a gated recurrent unit. Let me zoom in a little bit. I think we talked about these previously. I think these were, there were gated recurrent units in not BERT, but GPT-2? I think they were in GPT-2. It's a long short-term memory LSTM with a forget gate, but has fewer parameters as it lacks an output gate. Okay, so it's gated recurrent units' performance on certain tasks of polyphonic music modeling and speech signal modeling were found to be similar to an LSTM, have been shown to exhibit even better performance on certain smaller data sets. Okay, so you're still getting input, output, and then you have, input to the unit, output to the unit, and then you are forgetting things. So you have a forget gate, so you ignore previous information that's not helpful or is too old. Okay. So they're feeding that into a gated recurrent unit, and they have a series of them that are being fed in the context embeddings again, and then the previous unit. No, it's stepping through the words. I think it's stepping through the words. Where is the live chat? There it is. Okay, everyone's saying gated recurrent unit. It's like LSTM, but with fewer gates. Okay, very helpful. Thank you. Oh, Ryan's here. Hi, Ryan. And it's computed. So this is computed from the previous step, and memory, MP, so that is the output of the transformer encoder for P. Okay, I see. So we're sort of walking through our first, I don't know how these go together yet. Okay, so we're walking through our first sentence, and then we walk through the second sentence. We're using gated recurrent units to sort of keep track of our state. Okay. Okay, and we're doing, okay, so here we're doing softmax just over the trained embeddings and the given sentence. And for the second sentence, we're doing softmax over a second set of trained embeddings, I'm guessing. Okay, so we are training a vector and a matrix is what this looks like to me. And then a one-layer classifier is used to determine the relation at each step K. So this is as the GRU steps through, I think. And so at each step, we are, gotcha. Okay, so this must be no relationship. I'm guessing that this is where we are actually defining the three logical relationships. That's not the notation I learned for. Okay, so this is the dot product of these two. This is, I'm guessing, no relationship. This is probably contradiction, and then this is probably entailment. Okay, and then we use all the K outputs by averaging the scores. Oh, phew, okay. Okay, so our initial state is a summary of M, and then we go through K steps where we get the initials, we get our state from our previous step, and we take the softmax from some learned parameter based on our second sentence. We update, we take the output, that includes the previous step from our GRU, and then the learned parameter of, this can't be the same learned parameter every time. Okay, it's a computed from the previous state and memory. Okay, so we're starting with only looking at the hypothesis sentence, and then as we go through, we take in our previous state, and then the a new term that's computed from the previous state, and also the P, whatever that was, the premise sentence, and then we sort of go through. So over time, we have less and less information from the hypothesis sentence and more information from the parameter sentence is what I'm getting, kind of. And then at the end, and then each step we figure out what the current strongest hypothesis is. And then at the end, we average over all the scores. So we start only knowing about the hypothesis sentence. We have a hypothesis from that. So we have a softmax score out. And then we sort of go through K number of steps. And in each step, we have a little bit more information from our input from the second sentence. And at each of those steps, we take our what we most strongly believe to be the relationship, and then at the end we average over them. That's what I'm getting from this. 45 minutes later. No, it didn't take that long. Okay, that kind of makes sense. And then so the things that are learned look to be the weight matrix that we use to initialize the GRU, the weight matrix here. Sorry, I think that's a vector and that's a matrix. The weight matrix that we're using to get the softmax at each step. And then the final weight matrix is here, which is our hypothesis at each step, K. Okay, that makes sense to me. I don't know, I'm not 100% sure that that's what the math says, but I think that's what the math says. Okay, if that's all summarized over here, I'm gonna be so sad. Okay, no, that's training the whole model. And then each PR is a probability distribution over all of the relations, R to curvy R instead of even curvier R's. I have no idea how to read this. I'm assuming this is R. I have no idea. I have no idea what this means. I'm guessing that this is sort of like our belief of the current state given all the possible states. Oh. During training, we apply stochastic prediction dropout, presumably by the same author, before the above averaging operation. During decoding, we average all outputs to improve robustness. Okay, so they're also doing decoding? They've got a decoder? I thought they only had an encoder. Where are you decoding? Decode. That's the only time it's mentioned in the entire paper. I have no idea what decoder they're talking about here. Sassy says, is the first R relation and the second R real numbers? Very possible. I thought this was the R that meant real numbers. I don't know what the difference is, and I don't know how to Google one R looks slightly curvier than the other R. What's the difference in math terms? This is why it's easier to learn math in a classroom, IMO. Roman says, no relation is from relational algebra. Second R is the set of R relations. All relations. Okay, so we're getting the distribution of the specific set of relationships that we believe out of all possible relationships. Mm-hmm. That kind of makes sense. I feel like this is one of those things where it'd be easier to write it in words for people who are less in the field, but I'm sure that would be more time consuming for people who have spent a lot of time on this. I'm getting that this is what we are, that our output is how likely it is to be each of the potential relations, and then we just pick the one that's most likely. Okay. During decoding, we average all outputs to improve robustness. When are you decoding? Where is your decoder? There's no decoder here. You never talk about it again. I'm assuming that they're just being a little bit imprecise here, and decoding, I'm assuming when they mean decoding here is that they just sort of average these guys, like the final outputs, and the averaging improves robustness to not outliers. That's not what averaging does. I guess to sort of get the most probable when summing over probabilities. Okay, relevance rank output. So this is the one that they came up with for this task that isn't usually done as ranking, which is even further up here. So assessing whether a sentence contains the correct answer to a given query, which I think is usually, I would use that as do that as a binary classification task because the answer is either there or it isn't, which is how it's defined in GLUE. So this benchmarking data set of different tasks. But they say that they did it as a pairwise ranking task, where the model is expected to rank the candidate that contains the correct answer higher than the candidate that does not. We will show that this formulation leads to significant improvements in accuracy over binary classification. So I don't know the list of candidate answers. The model ranks them. Okay, so I think that the original task is to determine whether or not each sentence contains the correct answer. And here they are just ranking all the answers, and that their assumption, which seems like a pretty strong assumption, is that the sentence with the correct answer is going to be ranked highest. Which again, that assumes that one of the questions has the right answer. And this seems like it might be an approach that would only work well in this sort of little bit of a, what would you call that? It's a little bit artificial, you know? So Ahmed says, I think they mean while using the model in testing, not sure. Yeah, I think that's what they meant as well. It's just confusing because they're using a model where they could have a decoder and they don't. Okay, so that's the task that they're doing here. Take QNLI, so this natural language inference problem, as an example. Suppose that X is the contextual embedding of vector CLS, so like they've been doing throughout, which is a semantic representation of a pair of a question and its candidate answer. What? That's not ranking. Okay. So they've got a question, they've got an answer, and then they have a trained vector, and then they do sort of like binary version of softmax over that trained vector and the contextual embedding. So this is pretty much the same, except that we have a probability of relationship, I guess, or strength of relationship between Q and A. So the question and the answer. For a given Q, we rank all of its candidate answers based on their relevance scores computed using equation 5. So you do this a bunch of times for each answer in your set of potential answers. And then, oh, that's it. I guess they pick the top one. They don't actually say it, but I'm assuming they just pick the top one, whatever that is. Sure hope they show that improves performance, because otherwise that's just sort of a funky thing to do. Okay, the training procedure. The training procedure of MT-DNN, multitask deep neural network. I'm trying to think if there's any Muppets that would be very easy to fit this name into. I think this was a little bit before the big Muppet trend, because Elmo and Bert are Muppets, and I think someone had a Big Bird model. I think someone also did Ernie as a model. Oh, I see. So Ryan says, I think what they mean by the decoder is the outputs of the GRU at each time step. Instead of just taking the last output, they take the output at every step and then average. Yeah, I agree. I think that is what they're saying. Oh, the pre-training stage follows that of the BERT model. Oh, interesting. So they do pre-train the whole model and then tune each of these? In which case, the difference between this and BERT is not... Okay, let's keep reading. I think I have misinterpreted what the difference is between this and BERT, and I think that they're not doing what I think they're doing. What I said that they were doing at the beginning of the stream today. The parameters of the lexicon encoder and transformer encoder are learned using two unsupervised prediction tasks, masks language modeling and next sentence prediction. Okay, so they are doing full-on training of the model ahead of time. The difference is that they're updating the base model at the end when they do their task-specific fine-tuning, and not that the whole model is trained using task-specific fine-tuning. That's what I'm getting now. So I think I misinterpreted this. I think I misinterpreted their approach at first. Where were we? In the multitask fine-tuning stage, we use mini-batch-based stochastic gradient descent, SGD, to learn the parameters of our model, i.e. the parameters of all shared layers and task-specific layers as shown in algorithm 1. In each epoch, or epoch, I always say epoch, but I guess some people say epoch, a mini-batch BT is selected, e.g. among all 9 glue tasks, and the model is updated according to the task-specific objective for the task T. Okay, so we're doing a mini-batch, we're picking one of the tasks, and then we update the model based on the performance of the model and also the fine-tuning layer for that specific task. And then they repeat and they do, I guess, a bunch of mini batches. They don't say how many. I'm gonna guess a lot. That's just what I'm gonna go out there saying. Oh my God, more espresso. I don't know if you guys can hear it, but it's like shh. Okay. This approximately optimizes the sum of all multitask objectives. So I guess this is kind of transfer learning. Interesting. So algorithm, here's how they're training. So initialized model parameters theta randomly, pre-trained the shared layers, i.e. the lexicon encoder and the transformer encoder. So for this, you could straight up use BERT if you wanted. You don't necessarily have to do their pre-training. Set the max number of epoch max. Prepare the data for T tasks. For T in 1, 2 to the T, do pack the data set small t into mini batch d small t. So you're taking all your data, and before you train your model, after you've pre-trained your model and before you do your multitask training, you parcel up your training task. You parcel up your data for each task into a separate little mini batch. So sort of like I'm trying to think of a good example of what it's like. I guess it's like putting eggs in cartons. So if you have a big bucket of eggs you've collected and you put them in a bunch of cartons, and then you'll go through each carton one at a time, except you like mix the eggs from different types of chickens, I guess. I don't know. Maybe that's not the best metaphor. And then for each epoch in your number of epochs, merge all the data sets. So merge D1 and D2. Okay, and then shuffle D. And then for B and D, so B is a mini batch of task T. Okay, so we're merging so we're parceling into mini batches, we're merging everything together. So we're looking at all of our data in each epoch. Okay, right, that's normal. That's what epoch means, Rachel. And then for each of the little baby mini batches, we are going to look at only one task per mini batch. And what we'll do is we will compute the loss, and we will use different loss equations for each type of model. So for relevance ranking, we'll use this guy. For the pairwise text classification output, we'll use this unnecessarily, well, I shouldn't say that. I don't know that it's unnecessarily complex, but this part of the paper is clearly like the part of the first author's main research, like focus trajectory research program. That's what it's called. So this is like the first author's baby, I'm guessing, based on the amount of space it gets. And then we have the different equations that are defined here. So basically, we're taking some version of softmax over however many thingadoogles. classes, however many classes you're doing. Whew. And then we're computing the gradient, and we're updating the model. So you sort of always want to go down the gradient to get the lowest error overall. So interesting. So we're updating both the task-specific parameters. So here it's this, this vector, which is learned, that is task-specific, but also I'm assuming the embeddings, because remember from the BERT paper, or rather the BERT or the Viswani transformers paper, that attention has queries and keys, which are both learned and can both be updated in each training pass. So in each training pass, you update the task-specific parameters that you're learning, and then you also update everything back through the context embedding vectors. And it looks like also maybe the input embedding vectors. So everything's getting updated. And then in your next mini batch, you'll be looking at a different task, and then you'll be updating your task-specific parameters, but you'll also be updating the rest of the model as well. So that's what I'm getting from this algorithmic walkthrough. Ryan says, so each sub-batch is of a specific task, and we shuffle through the tasks. Yeah, that's what I'm getting. So in each epoch, you're going to see all of the tasks, but which set of data you look at for each mini batch for a specific task is going to be shuffled. Ahmed says, so we get an average of all the losses and use it to update the model, right? I think actually in each update will be based on one loss for one specific task is what I'm getting from the way they're describing this algorithm. And here they're just saying what the loss is depending on the specific task that they're doing. So over an epoch, you will be updating based on many mini batches. Each mini batch will have its own loss depending on the type of task that it is. That's what I'm understanding from this description of their algorithm. Okay, for the classification tasks, i.e. single sentence or pairwise text classification, oh, whoops, I said the wrong thing. It's actually down here and not up there. We use cross-entropy loss as the objective. In this study, we use pre-trained BERT models released by the authors. Okay, yeah, so where I said that you could use BERT here, maybe you should use BERT here and save the environment, use a little bit less compute. Where fancy one, tuxedo one, XC is the binary indicator 0 or 1 if class label C is the correct classification for X, and PR dot is defined by e.g. equation 1 or 4. Okay, so this is the probability that we're getting out. We're taking the log probability, and then the class label C. Okay, so we're taking the log probability and then using a binary indicator of whether it's correct or not. So if it is correct, we get a 1, I'm assuming, and if it's incorrect, we get a 0. So basically, did you guess good or not? And then we're doing this to it. Yeah. Roman says, I also understand it's a single loss per task. Ryan says, I don't understand what they mean by merging the data sets and then shuffle. I assume they just mean shuffling the order that we do each task and not literally shuffle all the data points. My assumption is that the squishing of things into mini batches, each mini batch is going to contain a different set of, well, I'm assuming it's random, so it might not be a different set, but should contain a different set of data. To pack the data set into mini batch D sub 2. So this is the model objective. Set T. Oh, maybe they do see all the data each pass. Surely not, right? Surely they wouldn't. Surely they'd. In each epoch, a mini batch is selected and the model is updated according to the task-specific objective for task T. Oh, maybe it is. Maybe they do see all the data for a specific task at each pass. I assumed they were subsampling the data in each pass, but I don't think it ever actually says that they do that. So you could be right, Ryan. And yeah, I think they probably are shuffling the order and not the data points. All right, for the text similarity tasks, such as STSB, where each sentence pair is annotated with a real value score y, we use the mean squared error as the objective, okay? Where similarity is defined by equation 2, that makes sense. So this is just like regular log loss, and this is just regular mean squared error. The objective for the relevance ranking tasks follows the pairwise learning to rank paradigm. Roman says the classification loss is the one you typically use. You can think of fancy one, XC, as YC, where Y is the one hot encoded label. That makes sense. So it's sort of like a little, I want to say Punnett square, but that's definitely not what it is. Yeah, that is helpful though. So we get a matrix out where it's sort of how good we did. Oh, I'm sorry, guys. I should have had one more coffee. I'm fading. Okay. What was I looking for? Okay, so mean squared error. The objective for the relevance ranking tasks follows the pairwise learning to rank paradigm. So it looks like this metric has been around for a little while, or, an eon according to machine learning research. Taking QNLI as an example, given a query Q, we obtain a list of candidate answers, fancy A, which contains a positive example, A+, that includes the correct answer, and A -1 negative examples. So yeah, they are making the very strong assumption that the set of answers that they are given is always going to include the correct answer. So this would work for something like a multiple choice question written by a human being for another human being, which I believe this stands for natural question answering whose it is. But it wouldn't work in a situation like scoring student essays where you're not guaranteed to have the right answer. We then maximize the negative log likelihood of the positive example given queries across the training data. Oh no. Okay, so here we're doing basically the same thing that we were here, taking the entropy loss for the probability that we got the right answer. So we want to make sure we get the right one, where that probability of getting the right answer is, wait, I know this now. This is softmax, but we're doing lambda, gamma. That's definitely either lambda or gamma. Gamma. Gamma rel, where this is defined by equation 5, and gamma is a tuning factor determined on held out data. In our experiment, we simply set gamma to 1. Why do you have gamma if it's just going to be 1? Okay, ignore gamma and don't use gamma. I guess they're using gamma because it was proposed by Burgess or Huang or whoever. So we're using basically just the output of equation 5, which is this bad boy. And okay, so we've got the relevance score for each of them. We take the softmax of the relevance score for the correct answer, and then that gives us the probability that we got the correct answer. Okay, that makes sense. That's very actually straightforward. I don't know why I was so intimidated. I do know why I was so intimidated. I looked down, I saw some Greek, I just started to panic. Oh my God, the rattling. Okay. Section 4, experiments. We're going to get down to some empirical results. Oh my God. It sounds like someone's unpacking like a China truck, like a truck full of China plates and such. I don't know if you guys can hear that. I can, very, very loudly. All right, we evaluate the proposed MTDNN on 3 popular NLU benchmarks, GLUE, Stanford Natural Language Inference, and SciTail. This is the first paper I've read that uses SciTail, but I'll take their word on it that it's popular. We compare MTDNN with existing state-of-the-art models, including BERT, and demonstrate the effectiveness of MTL for model fine-tuning using GLUE and domain adaptation using SNLI and SciTail. Using GLUE and domain adaptation. Okay, I'm not entirely sure where, so domain adaptation is you have like news text and you also want to work on models. So you're working across domains. So it looks like they're using, I'm not entirely sure why they're saying that GLUE is model fine-tuning and SNLI and SciTail are domain adaptation, but I guess we'll find out as we keep reading. Datasets. So I don't know that we're going to get all the way through all of these datasets. In about 7 minutes, and I am going to get kicked out of this room, presumably by the dish monster. No, that's not fair. People got to move dishes around. That's fine. The GLUE benchmark is a collection of 9 NLU tasks, including question answering, sentiment analysis, and textual entailment. It is considered well-designed for evaluating the generalization and robustness of NLU models. Both SNLI and SciTail are natural language inference tasks. All right, and we have previously read about GLUE, I believe, in the BERT paper for the first time, and I think the GPT-2 paper also looked at GLUE and then a bunch of other tasks and also had like kind of not amazing performance on a lot of them. You may want to go back and rewatch those videos if you're deeply curious about those models. All right, COLA, the corpus of linguistic acceptability, is to predict whether an English sentence is linguistically acceptable or not. It uses Matthew's correlation and coefficient as the evaluation metric. And I believe that the linguistic acceptability judgments here are being done by linguists, but I don't care enough to go and look it up and check. SST is the Stanford Sentiment Tree Bank to determine the sentiment of sentences. Sentences are extracted from movie reviews with human annotations of their sentiment. Accuracy is used as the evaluation metric. Semantic textual similarity benchmark is a collection of sentence pairs collected from multiple data resources, including news headlines, videos, and image captions, and NLI data. Each pair is human annotated with a similarity score from 1 to 5. Oh, I suppose that it was 0 to 1 earlier, and I was wrong about that, indicating how similar the two sentences are. The task is evaluated using two metrics, the Pearson and Spearman correlation coefficients. So they're just doing 2 types of correlation. QNLI, this is derived from the Stanford question answering data set. I don't know, I'm trying to read the citation now, even though I haven't read any of the other citations, which has been converted into a binary classification task in GLUE. A query candidate answer tuple is labeled as positive if the candidate contains the correct answer to the query and negative otherwise. In this study, however, we formulate QNLI as a relevance ranking task where for a given query, its positive candidate answers are considered more relevant and thus should be ranked higher than its negative candidates. This is the thing that I'm most skeptical about in this paper. I think their overall architecture is fine and seems extremely reasonable, and I'm interested to see the empirical results. This dude, though, why? Why are you assuming that there is going to be a correct answer? That seems like too broad of an assumption. QQP. The Quora question pairs dataset is a collection of question pairs extracted from the community question answering website Quora. The task is to predict whether 2 questions are semantically equivalent. As the distribution of positive and negative labels is unbalanced, both accuracy and F1 scores are used as evaluation metrics. Was there a title competition about this? I know there was one on whether or not the the particular question was sincere or if people were being butts. Kaggle question pairs. Let me zoom in a little bit. Zoom, zoom, zoom. Can you identify question pairs that have the same intent, semantically equivalent? Yeah, I think this is the same thing as was done in this Kaggle competition 2 years ago. So that would have been, let's see. Core question pairs, no citation, no other information, no DOI, no link to the paper. So 0 out of 10 on citation practices. Maybe 1 out of 10. They did cite it, but I could not find this paper just based on this information very quickly. Not a fan of that. MRPC, the Microsoft Research Paraphrase corpus, consists of sentence pairs automatically extracted from online news sources with human annotations, denoting whether a sentence pair is semantically equivalent to the other in the pair. Similar to QQP, both accuracy and F1 score are used as evaluation metrics. MNLI, the multi-genre natural language inference, is a large-scale crowdsourced entailment classification task. Given a pair of sentences, i.e. a premise-hypothesis pair, the goal is to predict whether a hypothesis is entailment, contradiction, or neutral with respect to the premise. The test and development sets are split into in-domain, matched, and cross-domain, mismatched sets. The evaluation metric is accuracy. RTE, the Recognizing Textual Entailment dataset, is collected from a series of annual challenges on textual entailment. The task is similar to MNLI, but uses only 2 labels, entailment and not entailment. The Winograd Natural Language Inference, this is the one that GPT-2 did super bad on, is a natural language inference dataset derived from the Winograd Schema dataset. This is a reading comprehension task. The goal is to select the referent of a pronoun from a list of choices in a given sentence which contains a pronoun. SNLI. The Stanford Natural Language Inference dataset contains 570,000 human annotated sentence pairs in which the premises are drawn from the captions of the Flickr 30 corpus and hypotheses are manually annotated. This is the most widely used entailment dataset for NLI. The dataset is used only for domain adaptation in this survey. And Ahmed has helpfully posted a link to it's not a paper, it's just a dataset, just a blog post. You can cite the URL of the blog post. I'm not entirely sure if this is, okay, so it looks like this is maybe not the same dataset as the competition, because that was published before the competition. And then SciTail. This is a textual entailment dataset derived from a science question answering dataset. Not at all 2018. The task involves assessing whether a given premise entails a given hypothesis. In contrast to other entailment datasets mentioned previously, the hypotheses in SciTail are created from science questions, while the corresponding answer candidates and premises come from relevant web sentences retrieved from a large corpus. Oh, I think I have heard of this. As a result, these sentences are linguistically challenging, and the lexical similarity of premise and hypothesis is often high, thus making SciTail particularly difficult. This dataset is used only for domain adaptation in this study. Okay, so I think the difference here between multitask learning and domain adaptation is whether or not you use the specific task to update the weights of your embedding vectors or not, I think. Okay, it is 4:01 and I am going to get kicked out of this room, literally right now. Thanks so much for joining me, guys. I'm going to wrap it up here and I will be back on Friday for live coding, and watch out for the announcements for that. How do I end the Hangout? Thanks for joining, guys. I'll see you on Friday.